Hi everyone, this is Mr. Zarzak, and in this screencast I'm going to talk about the rules for dealing with what we call parallel circuits. Let's get started. Okay, so here's a simple parallel circuit. If you remember, this here is just our voltage source, so this can be a battery or power supply. I've got a conducting path or a wire that comes out of the battery, and then at this point it splits up to where there's two conductive paths. Okay, so when we draw these parallel circuits, drawing the resistors in this manner is where the parallel circuit gets its name. And here I've just got two resistors drawn in parallel, but there's no reason I couldn't add more. So if I wanted to add, say, another resistor in parallel, now there would be a third one, and here's a fourth one. Okay, and we could just keep going on and on and on, and you draw it probably a little nicer than I just did there. Okay. What's neat about the parallel circuit is its behavior is actually kind of the opposite of the series circuit, whereas every time we add a resistor in series, the total resistance of the entire circuit actually goes up. We actually find that with the parallel circuit, the exact opposite happens. Every time we add a resistor in parallel, we're effectively decreasing the resistance of the circuit. Okay, so these two configurations give us different ways to build circuits with whatever kind of resistance that we want. Okay, let's see why it works this way. Okay, so let's just go back to a parallel circuit with two resistors. Starting with the current. Okay, so you have to imagine the total current just flowing out of the battery from the positive terminal. Okay, so I'm just going to label that IT for the total current. Okay, well, when we get to this branch over here, the current has two options, and so what's going to happen is the current is going to split. If the two resistors happen to be the same value, well, then the current's going to split evenly between them, but if they're not, well, then the current's going to split unevenly. If I look at my two resistors, I'm just going to call this one R1 and this will be R2. Okay, well, that means that part of the current is going to flow through that first resistor, so I just call that I1, so I'll just label that here. So there's I1. Okay, and then part of that current is going to flow through I2, so then I'll just label that I2. Okay, from Ohm's law, which is just V equals IR, for a bigger resistor, you're going to wind up with a smaller amount of current flowing through it. So in other words, if R1 is, say, bigger than R2, well, then I1 would actually be smaller than I2. What's important here is that we have conservation of charge, so that when the current splits up between the two resistors, okay, that split's really just coming from that total current here. So part of the current goes through this, part of the current goes to this, and then when it comes back together up here along this conductive path up here, we just got I total again. Okay, so using this logic, we can write a general equation that just says that the total current in a parallel circuit is just equal to the sum of the currents that flow through the parallel, what we call them branches of the circuit. Each one of these is a branch that the current can follow. If we add more resistors, okay, well, then that sum would just be I1 plus I2 plus I3 plus I4 plus however many individual current pieces we have, all of which must add up to the total. The other key to understanding parallel circuits is how the voltage drops across any resistors in parallel winds up being precisely the same. And here's what I mean by this. Okay, so if I start here at the battery, this right here is just a wire or a single conductive path. And even though the conductive path splits, okay, everything I've just highlighted is all along the same wire or set of wires or conducting path. And a good conductor is really just a material where there's no change in voltage. So everything that I've highlighted here in blue is the same exact voltage, okay, that's provided by the positive terminal of the battery. Now, if I look on the other side of my resistors, look what happens. If you look at what I'm highlighting here, okay, that's also one single conducting path. And so the deal is that, well, the current winds up splitting up. So the current flows out of the battery over to here, and then it splits up into two parts. Okay, but then it comes back together. The key is that across all of these resistors, in this case there's just two, but across these resistors in parallel, the voltage drops are precisely the same. So we have the exact same change in voltage. If we think back to what we know about voltage, change in voltage is just a measurement of the change in the potential energy per unit charge. Okay, and what that means is that regardless which resistor any charge flows through, if they're wired in parallel like this, they will each experience the same change in potential energy. So just to kind of use the labels that I used before of R1 and R2, whether a current flows through R1 or R2, the voltage drop across each resistor will be precisely the same. Remember, what we know about energy, okay, is that it's a state function. The path that the current takes to go from what I've highlighted in blue to what I've highlighted in red, it doesn't matter. The change in potential energy per charge for any charge moving through those resistors will be the same, and hence those charges will experience the same change in electrical potential, which is just the change in voltage. So this kind of gives us two different ways to think about it. Okay, remember again, okay, that everything here in blue is just one single conductive path along the same voltage. And everything here that I've highlighted in red is another conductive path which would also be on the same voltage. Whether charge goes through R1 or R2, it experiences the same voltage drop or change in voltage. And we remember this is that voltage, the change in voltage is equal to the change in potential energy per charge. Energy is a state function. It's not path dependent. How you get from the blue to the red is irrelevant. The charges that move through either resistor lose the same amount of electrical potential energy. And so to sum this up all into a very simple rule for voltage across a parallel circuit, the total voltage is equal to the voltage drop across resistor 1, which is equal to the voltage drop across resistor 2, and the trend would continue if I added more resistors. If there was 3 resistors, Vt is equal to V1, is equal to V2, is equal to V3, and so forth. The way we add up resistors in parallel is a little bit different than series. To do so, to get this total resistance, okay, we're actually going to go back to our current rule, which just says that the total current flowing through this particular circuit would just be the sum of the pieces of current that flow through the two resistors. So I total is equal to I1 plus I2, where I'm just going to call this one R1 and this one R2. And I've got part of the current flowing through this first resistor here. That's just our I1. And the rest of the current is flowing through this second resistor here. That's I2. And then these two individual pieces just add up to this thing that we call IT, the total current. Okay. Now, if we remember that Ohm's law just says that voltage is equal to current times resistance, okay, well then I can take and I can rewrite that equation just as current is equal to voltage divided by resistance. Okay, so that's the first trick. And then the second trick is that the total voltage in a parallel circuit is the same as the voltage drops across each of the individual resistors. So the voltage drop across resistor 1 is equal to the total voltage provided by the battery, as is the case with the voltage drop across resistor 2. It's also equal to the voltage drop across the battery. So now I'm going to use a little bit of substitution. Anywhere I see an I, I'm going to replace it with a V divided by an R. So if I just jump back to this total current equation, look what happens. I replace IT with VT divided by RT, but I'm not going to stop there. I'm going to replace I1 with V1 over R1 plus V2 over R2. And if I look back one more time over here, the total voltage is the same as V1 and V2, so I'm actually going to take and now substitute out V1 and V2 with just that V total. So all I'm really doing is just replacing subscripts, but when I do, okay, look at what happens here. I've got this case where I've got V total in the numerator of all three parts of this fraction. That means that I can take and factor that numerator right out, cancels right out of the equation. I'm left with this. 1 over R total is equal to 1 divided by R1 plus 1 divided by R2. And if I had 3 resistors in parallel, then it would be 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and the pattern would repeat. Okay, so what this does is this gives me a way to calculate for the total resistance of a parallel circuit. The one tip I'll give you is that when doing these calculations, at the very end here, the equation gives you a solution for the inverse of the total resistance. And so if you found this value, you'd have to take the reciprocal of that to find the actual value for the resistance of the circuit. You'll see this when we practice in a moment. So to summarize my rules for parallel circuits, the total voltage that's provided by the battery or the power supply is the same across each pathway, no matter how many resistors I have. So if I added another resistor, okay, there'd be V1 is equal to V2 is equal to V3 is equal to V4 is equal to V5, and so on and so forth. The total current that flows out of the battery just splits up amongst the resistors, and the sum of the currents flowing through the resistors is just equal to that total current. And then finally, we have this special equation that we use for total resistance, where 1 over the total resistance is equal to the sum of 1 over R1 and 1 over R2 plus 1 over R3 plus however many resistors we have in parallel. Now that we've reviewed the rules for dealing with parallel circuits, then now would be a great time to go and practice. So these are the practice problems that we're going to work in class. All right, so why don't you go ahead and give those a try. These are the kinds of questions that you'd be asked to solve for with parallel circuits: finding total resistance, the voltage across each resistor, the total current, and then the current through the individual resistors. Good luck, everyone. This is Mr. Zarzik saying thanks for watching, and I'll see you in class.